Okay. In the break, there were fundamentally two questions. One was about the gray lines in this other figure. What do these gray lines mean? And I'll try and say it again. Yeah? So we have, in a Gaussian process, an infinite collection of random variables. For now, let's say this is x. For now, I'm only considering 3 of these random variables. Here I've arbitrarily decided to take these random variables located at the vertical bars that you see here. So I'm interested in this random variable, and in that one, and in that one. My basic assumption was that I'm looking at a Gaussian process, so any subset of random variables, including these 3, must have a joint normal distribution. And the formula for this distribution was given here, and I had shown how to compute this sigma. So the entries, one entry of sigma here is just reading off from this function at the distance given by the sites where I'm trying to make these observations. So between this random variable here and the next one, these have a distance of 1. So I'm reading off here how much correlation do they have. And I'm putting this into the covariance matrix as the cross in the responsible element between these two random variables. So I have a 3D Gaussian distribution, and I can always sketch this 3D Gaussian distribution, and it's shown by this ellipsoid that we saw here. Now, from this Gaussian distribution, so far there are no observations in the game. Instead of drawing an ellipsoid, I can also draw a few samples from this distribution. And I've done that, so I've drawn a red sample and a blue sample and a green sample. And this is a 3D Gaussian, so if I draw a green sample, this means I get out 3 observations. Or the red point here corresponds to 3 observations, so shown by these dots here. Now, we also know that these random variables, they are dense on the line. So in principle, I should not look at a 3D Gaussian, but at an infinitely dimensional Gaussian. And if I draw samples from this infinitely dimensional Gaussian, I will get these continuous lines here. So 3 samples from this super high dimensional Gaussian would be these 3 functions that we see here, the green and the red and the blue. Now in the picture above, a few samples were drawn, but these samples here were simply shown in gray and not in red and green and blue. Okay, so these are just samples from the prior. That was the one question. And the other question was, why fish and dog and cat? And I'm sorry, it's just that in this paint program, I did not know how to write x1, x2, x3, but it was easy to put the cat and dog and fish. Okay, it's the only reason. So we know that variable names don't matter. Okay, so dog is x1 and cat is x2 and fish is x3. And in the next iteration, I think I will put maybe blobs or Roman numbers or something instead of these confusing animals. Excuse me. But at least some people had a good laugh about this. Good. So more questions. All right. So now we are interested in actually finding this conditional distribution. I had shown this conditional distribution here. This was this skin-colored or whatever, orange distribution. And now let's compute it for real. So I have a prior. Y follows a normal distribution with mu and sigma. And this sigma later, we will partition it, and also the y will be partitioned. I'm first collecting all the random variables for which I have no observations, yu, and the random variables where I do have observations, the yl. so I've arranged them in this order in my vector y. And then I can partition sigma accordingly. So I can write this as a concatenation of 4 blocks: sigma uu, sigma ul, sigma lu, and sigma ll. Okay. And we will also need later the precision matrix, which is the inverse of the covariance matrix. And I can similarly partition my precision matrix into these 4 parts. Now, unfortunately, oh, sorry, I should, this one would be again PUU, and this here should be PLL, and the rest is correct. All right. Unfortunately, and we're very sad about this, PUU is not the same as sigma UU to the -1. If it were, then the math would be a whole lot easier. Okay, but unfortunately, it's not true. So, what we want now is the conditional distribution of YU given YL. So I'm writing here the probability of YU given YL. I can always write, I can always write a conditional distribution as the joint divided by the marginal. So this statement here is generally true. And knowing that these are all Gaussians, I have, written them here, omitting the normalization constants. Strictly speaking, I would have to show that in the bottom, this marginal distribution of the YL, that it has this form. But I'm just pretending for now, or saying that it is this way, and it's actually not hard to show. All right. Now, I am writing out this expression in more detail. Just instead of y, I'm now writing this partitioned vector, yu and yl. And instead of p, I'm giving you here this partitioned form. And I'm doing the same for the numerator, which is this, and for the denominator, which is that. To make my life a little bit easier, I'm going to call this part here A, and I'm going to call that part here B. And then I'm writing the very same thing, just with A's and B's instead of the Y's minus mu's. Okay, just to have to write fewer characters in what follows. All right. Then in the next equation, I have multiplied out all the terms that were written in the numerator. I get this. And I find that one of these terms cancels with what was in the denominator. And moreover, this term here is the same as that term there. So summarizing, I get this. And if I now substitute back for what was A and what was B, I get this expression here. Now, note that here we have PUU and PLU, and I said that unfortunately PUU is not just sigma UU to the -1. But the proper formula can be found, for example, in the matrix cookbook, equations 399 and 400. So that these equations are true. I'm not proving it here, but you can verify it. So if you insert the definition of C1 and C2 in this thing, you get a matrix. And if you then multiply it with this thing here, you will get the identity matrix. So showing that, yes, indeed, this was the proper inverse. Now, for our purposes, we are interested in, so we need PUU and PLU. We also know that sigma to the -1 is P. And we said that P itself was we had said that P itself can be partitioned as PUU, PLL, PLU, and PUL. And so we need this term and we need that term. And now I'm looking up in the matrix cookbook. There are two equivalent expressions given for PUU. I'm going to use this one here. So this is going to give me PUU. And that one there is going to give me PLU. All right. Using these results from the matrix cookbook, I am rewriting this conditional density here, except that I've replaced PUU and PLU by the expressions that I find here. And, well, the result is shown here. And the main thing to note is that this matrix here, which is called C1, also appears there. So far, so good. Now, on the other hand, I can write very generically the following. I can say that I have some conditional distribution of YU given YL, and I know that it's Gaussian. So I'm simply writing a Gaussian here where I have written that, well, what a Gaussian does is it always measures the deviation of the variable from its mean. It's quadratic in that, and I scale by the inverse covariance matrix. I scale by the precision matrix. So I can simply write this equation. The problem being that, well, what is the conditional mean and what is the conditional covariance matrix, that these are unknown. Okay, so what I mean by this notation here, this is the inverse of the conditional covariance matrix. UU given my observations at the sites L. So this is nice and elegant to write, but well, all the hard parts are missing. Okay, so I've just given names to those solutions, but now we need to give life to those names. To give life to those names, you see that this is the same as that. So we're now going to compare coefficients. I'm starting by collecting coefficients which are quadratic in YU. So from the equation above, the only term which is quadratic in YU is we take this YU, we take that, and we take that YU. And this is what's written here. On the equation on the bottom, well, the term which is quadratic in YU is YU times this times YU, which is written here. Now, these distributions are meant to be the same. So, well, the beginning looks the same, the end looks the same, so the middle thing must also be the same. Yeah, so the finding is that my conditional covariance matrix is this expression here. And what's noteworthy is that it depends only on the locations of the observations, but not on the observations themselves. let that sink in. That's a really important result in Gaussian processes. So this conditional covariance matrix, it describes the uncertainty of my predictions. And this uncertainty depends only on how far are we away from the other observations, but it does not depend on the observations themselves. So if there are a few things that you remember from today, please make this one. I don't mean the formula, I mean this statement here. Good. So we were saying that we need, in this generic or formal equation, we need to find the conditional mean and we need to find the conditional covariance matrix. The conditional covariance matrix we have just found remains the conditional mean. To find the conditional mean, we now look at the terms which are linear in YU. So from the first equation, what is linear in YU is going to be this term here. Yeah, so something like mu, and then a complicated sigma, and then a YU. And I've been writing the same thing in green here. But there's also, from our former denominator, there are more terms which are linear in YU, namely, all of this is linear in YU. So I'm also writing that down in blue. And then, well, you see that we can multiply out this because we find it on the right-hand side of both the summands. So I've pulled that out. Okay? So these were the terms which were linear in YU. And now we look again at our generic equation and find the term which are linear in YU, which is this one here. And now we again compare. So this y and this y are identical. This and that are identical. So in other words, the conditional mean that we have been looking for must be this. And that's the boxed equation. Our conditional mean is this. Complicated looking equation. We can look at it in the special case that if we assume that all of these mu's are 0, then the equation simplifies to this. Or if you prefer thinking in terms of kernels, then that's how I would write it. So we now know that our predictions, y hat, are going to be given by the following. We're going to take our observations. We will multiply them with the inverse of the covariance matrix between the observations, and we multiply it with the covariance between our prediction sites and the sites where we have measurements. It's maybe written a bit more clearly here, because here it's written in terms of the UL and the LL. So we see that these are actually matrices here. So what's the big picture? The big picture is that we wanted to find the conditional mean shown by the thick black line, and we wanted to get an estimate of the conditional uncertainty, which is here sketched in red separately for each random variable. So these were the things that we wanted, and we now have them in terms of these two box equations. This one here, the conditional covariance, and this one, the conditional mean. Breathe. So in summary, we've spent 20 minutes and a lot of equations to show the following. This is a tiny excerpt from, if you open the Wikipedia page on multivariate normal distribution, there's all kinds of things. And one of the subheaders is called conditional distributions. And if we zoom in, we see that these things now look familiar. It's what we have just been deriving. So we've started here from first principles, except for using the matrix cookbook. All right, and let me stress that we now have a concrete recipe, okay? The concrete recipe for mu equals 0 is given by these equations here. So what do we have? These were the observations. These were the covariances between the observation sites. And they are given by our choice of kernel, for example, the radial basis function. These are the covariances between the observation and prediction sites. So, in other words, this matrix I can just assemble by looking up its elements in terms of my, for example, radial basis function. Same for sigma LL. The hard computational work is this. I need to invert this matrix. But that being done, I get an effective vector which I multiply with my observations to get my prediction out, which actually in this form is linear in the observations that I made. So we now have a concrete computational recipe to find this conditional mean. So even if even if you do not follow the derivation, what we have here in these boxes is a concrete computational recipe to find the posterior mean and the posterior uncertainty. All right, do you have questions at this point? Yes?
What is the mu?
What is the mu? Going way back up. Our assumption was that the observations are realization of a multivariate normal with mean mu and covariance structure sigma, and we assume mu and sigma known. Very often in the literature, you just say mu is assumed to be the mean of all your observations, or mu is assumed to be 0 if you have that kind of prior knowledge. Yeah, so what will happen is that far away from all observations, let's look again at this picture here. Far away from all observations, your prediction will revert to the mean. So if you started with mu 0, then it will go to 0 as we go away from all observations. If you had pretended that mu is -3, if somebody had told you that the truth is that mu should be -3, well, then away from the observations, it would go to -3. But also, by the way, it would also look a little bit different between the observations. So it would try and return to the mean even between the observations. Yeah, but in terms of the formula written further down, so this thick black line here, that's mu unlabeled given labeled. And what I've shown in red here, let me call it, is the variance sigma squared of unlabeled given labeled. So this would be the diagonal elements of this sigma squared UU given L, or sigma UU given L. More questions? Okay, so if we assume that mu is 0, the only thing that you need to understand in order to implement Gaussian processes for yourself is where do these elements of capital sigma come from. Yeah? And these elements of capital sigma, we had this further up, are given in terms of whatever covariance function you have decided to use. If I use this RBF kernel, then to find the one element of this matrix sigma, I need to only look up how far away are these two random variables. And then if the two random variables are, for example, at a distance of 2, well, then I read off from this graph what is the amount of correlation that I expect at a distance of 2. And then I put this in the corresponding element of my matrix. So if you understand, or if you just follow this, then the rest is just a computational recipe that you get out here. Yes?
Where exactly do I put it in the matrix? Because the matrix you wrote down there only had ones and e's as far as I could see. So
okay.
Which variable is replaced?
So why was it ones and e's? Because here I had considered, in this example, I had considered 3 locations: x1, 1, x2, 2, and x3, 3. Yeah, so this is why you see I had these 3 vertical lines. But for the sake of argument, let's make this a bit less symmetric. Let's say that 1, 2, and whatever, put this at 5 or something. Yeah? So let's say 1, 2, and 5. So far, so good? Now, I'm now interested in this covariance matrix. Let me draw it here so that it's separated from what we had before. And I'm calling these random variables here x1, x2, and x3. So I'm first looking at this element 1, 1 of this matrix. x1 and x2 have a distance of 1. Yeah, so I'm now using this recipe, let's say this RBF kernel here. So I get e to the minus 1. Or excuse me, the diagonal element, that's wrong. That's the distance between x1 and itself. So I get e to the minus 0. Between the first random variable and the second, I get e to the minus 1. Between the first and the third, I get e to the minus, they have a distance of 5. No, not true. They have a distance of 4. I get e to the minus 4 squared. for the next element, this is now for the second random variable. Its distance to the first is 1, so I'm reading off that it's e to the minus 1. The distance to itself is 0, so it's e to the 0. The distance to the third random variable is 3. And then I do this for one more line for the third random variable. And well, I can also complete this by symmetry because this whole thing is symmetric. So to find these numbers here, I've always used whatever kernel I have decided to use. Yes?
So should it be 1 over e to the 4 on the left-hand side because we have a distance of 2 and we have a square? Because if you use a wave function, we have not distance, but a distance squared, and we have x minus x prime. So x minus x prime, the 1 to the e squared case would be 2, but if you would work the square, it would be 2 to the square, and to the power 2 is.
So let's talk about this case here. Yeah? This is x1 versus x3, and so I'm using e to the minus x3 was located at 5, minus x1 was located at 1. So this is why I wrote e to the minus 4 squared.
Yeah, but I mean the left example with 1 and 1 over e and 1 over e squared.
Ah, I made a mistake over there?
Yeah, I think so. Because if you have 1, then 1 over e, then it shouldn't be.
Okay, it should be 4. Thank you. Like this, yeah? Thank you. You're right. Sorry. Okay, so we have a recipe, yes?
Can you give maybe a heuristic explanation how we can see from the continuity of the kernel the continuity of the because it derives from if we do a continuity of all of this, right? Then we get the continuity of our kernels.
Yeah.
Can you give a heuristic explanation, maybe a short one?
Yes.
How we can see this?
So, are you familiar with the Wiener-Kindchen theorem?
No.
Which says that, and it's easy to show actually. The Wiener-Kindchen theorem says that the power spectral density of a stochastic process is given by the Fourier transform of its covariance function. And whenever we have a covariance function which is not everywhere differentiable, this will lead to the power spectral density decaying more slowly. And a power spectral density which decays slowly with high frequencies means it's very rough. We can do something even worse. We can have a covariance function which not only has a cusp, but actually has a jump. I think this was also you asking the question earlier. So if we have a covariance function which has a jump, this means that my power spectral density will decay only as 1 over x, or 1 over frequency. So it will have even higher frequency content and be even rougher. Yeah? More questions? All right. Then I want to give a few comments. I'm copying again this equation here. in what I will say next, I will assume for the moment that my query sites and my label sites are equispaced. You know, in all of the derivation, we did not make the assumption that they are equispaced, but here we do. And then I can have two interpretations. My first interpretation would be that this thing here is a low-pass filter. Because if you look at an RBF kernel, that's a smoothing kernel. If we take its inverse, we get a high-pass filter. So, in other words, I could say that these are the weights that I'm going to use for my overlapping basis functions. Which are given by my kernel. So, in other words, when I have, in the example above, I had said, okay, I have observations at the locations 1, 2, and 5. Then effectively what I'm saying is that I'm using these basis functions, maybe RBF kernels. And now my prediction, mu of u given L or y hat, my prediction is just a linear combination of these basis functions. But I need to correct for the overlap of the basis functions. And I do this in terms of this high-pass filtering. So interpretation 1 is that prediction is a linear combination of basis functions k, which are located at my observation sites. And what I've called the high-pass filtering corrects for the overlap between the basis functions. That's interpretation 1. My interpretation 2 this was not good. My interpretation 2 is that I'm getting here an effective basis function. So I would say that the prediction is a sum of effective basis functions and I'm simply weighing these effective basis functions by the observations themselves. And here is a picture. So I have X, I have Y, and I now have observations at 3 locations. These are my observation sites x1, x2, and x3, not equispaced. And I can now compute these effective basis functions which are shown here. And they have a number of interesting properties, namely the effective basis functions. They are always 1 at the site of their own observation. And they're always 0 at the locations of all other observations. So it's 0 here and 0 there. And the green one is 0 here and 0 there. And the red one is 0 here and 0 there. So this structure is not accidental. Good. Another comment. Yes.
These basis functions, where did they come from? Like, are they? Do we just assume that the basis functions look like this, or?
Yes.
Are they?
So the original, in this interpretation 1, yeah, these original basis functions are just your kernel K that you have assumed from the beginning. Yeah.
But the effective basis functions are just, or this doesn't read the results of the calculations with those
Yes.
basis functions used.
Exactly. Yes. The effective basis functions are the result of the calculation that correct for this overlap. So they depend on what basis function do you assume, what kernel do you assume, and on the relative spatial location of your measurements. Good. Next comment. What if my measurements are noisy? So we can say that YL was generated by some normal distribution, mu L, and it has this covariance structure. So we have this correlated kind of noise, plus we have a little bit of white Gaussian noise as measurement error. So this is the assumption that I'm making. What I find then is mu u given L is mu u plus sigma ul. This is like before, but now I'm adding here a little bit of identity matrix. And this, of course, reminds you very much of ridge regression. So what we have here, one way to look at this is to say that we're doing kernel ridge regression. The interesting thing is that this mu L here, normally it's interpolating. If we look at the conditional mean here, the thick line, this was an interpolation of my measurements. If we now assume this measurement noise, then I get something which is no longer interpolating. So now this is going to approximate my data, and I'm usually getting something much smoother. It no longer interpolates my observations. So what I get overall is a smoothing effect. All right, and then I have a few pretty pictures for you left. There's much more to say, of course. But what I have here is a 2D example of effective basis functions. where I assume that the measurements are performed here at this grid, and you can see that this effective weight function now becomes a function of space. In the middle, we're going to use a different interpolating kernel than on the outside. And because we have this uncertainty measurement, we can now use this for experimental design. So for example, if we have, let's say that we want to explore this one-dimensional space, and we ask ourselves, where should we perform our measurements, assuming a certain smoothness of our stochastic process? Then I can start with some initial sampling pattern. Let's say we sample here, here, and here. And I can compute for this sampling pattern what is the estimated uncertainty. And now I can say, fine, I want to minimize the integral of this estimated uncertainty. And if I do gradient descent under this objective, then you can see here how these points evolve over time. And you see that for this particular problem, I would find that good locations to sample are here, here, and here. We can do the same in 2D. We can say that, for this domain, where should I sample in order to minimize the integrated mean square error? Well, and the answer is at these locations. Or we can do this in infinite spaces and ask, if I have to sample an infinite space with an infinite number of points, where should I sample? And the answer is, and that's now not a hand-waving answer, this is proven, that if you have a rough process, then you should use the best packing lattice. If you have a smooth process, then you should use the Fourier transform of the best packing lattice. And finally, you can use this for sequential experimental design. Let's assume that we have this space, and we have in this space some unknown objective function. So perhaps this means, where can oil be found? And in this picture here, the way I've drawn it, lower is better. So we want to find the minimum of this unknown function. So we're starting by sampling, let's say, at these locations. And I find these observations. Given these observations, I can update my estimate of what do I think is true, which is here shown by the red line, and I can update my uncertainty estimate. And then I can say, fine, I'm looking at this uncertainty estimate, and I'm interested in finding even lower values. So here I'm looking at the lower envelope of this curve. And I'm asking, where does it attain its minimum? It attains its minimum here. So I'm performing another measurement on this very left-hand side. And I now get, the information that actually that was not so interesting, but I can update my estimate and my uncertainty estimate. And I can do this repeatedly until I have, with a few measurements, sampled my function well, especially in areas of, where it attains low values. Now, in one dimension, this is not so interesting, but if you work in high dimensions. So for example, people are really using this to optimize engines of cars. And you have a high dimensional parameter space of how do you have so many parameters in tuning your engine. And you cannot try out systematically all these parameter settings. But you want to, let's say, minimize the amount of exhaust produced. Then you are interested with the minimum number of measurements to find a setting of your parameters which will minimize the amount of exhaust produced. And then you can use this kind of scheme in this high-dimensional optimization problem of optimizing your engine. And I know for a fact that people are really doing this at a major company in the Stuttgart area because some former lab members are doing this for a living now, quite successfully. Very good. Sorry for the overtime. Thanks for your interest. See you soon.